Okay, so what we will be doing is quantum mechanics. A bit more complex with some new tools, let's say. So what do we do in quantum mechanics? Well, we have the Schrödinger equation. Let me write it in this way. This is what we do. This is the equation that we solve. Well, of course, we restrict ourselves in quantum mechanics. We say that our state can be written in terms of some eigenstates, which quite often we choose as the eigenstates of the position operator. Summed over all possible values of x. Well, x can be, in fact, any quantum number that you like. And this is the wave function that you usually use. And then you say that, okay, this wave function, if you also add the time dependence, now, what is the Hamiltonian? Well, typically you have minus h bar p squared over 2m, h bar squared over 2m, Laplacian plus v of x. Now, this is one dimension. You can just generalize it to 3 dimensions. Quite often in field theory books, you will see the comment that, well, we have to work with field theory because we cannot describe particle creation and annihilation in quantum mechanics. Well, that is not something I would agree with, in the sense that, you see, what I did here, this is my Schrödinger or whatever equation you want to call it. That is quantum mechanics. So it just, I have these abstract states. There's an operator called the Hamiltonian operator, which determines the time evolution of my whatever states I have. Then in this state, I already said that, okay, my states will be just single particle states. There's no other possibility. So I already restricted myself to single particles. I don't have to do that. For example, I can say that I will have states of this form. I can have such states. I can construct so-called my Hilbert space in terms of such states where, okay, the first part has one particle in it, the second part has two particles in it. Of course, in that case, I cannot really write my Hamiltonian in this form, because here, this Laplacian, or let me write it as the derivative, it's just a derivative with respect to one coordinate. Which coordinate? It doesn't. That operator doesn't make any sense on this state. So what is usually done in this case is I write my Hamiltonian as one part that acts only on one particle state. I have another part, the second Hamiltonian, which acts only on the two particle states. And then I should have some interaction, some transition between those two. And my Schrödinger equation, well, this matrix notation makes it easier to write down the equation explicitly. And then my matrix equation will be I h bar del over del t, my Schrödinger equation, phi of x1, phi of x1, x2. This is equal to h1 v h2 phi of x1 phi of x1 x2. Or let me write it even more explicitly. Well, I still need to do a bit more work in the sense that this product should only depend on x1 and this product should only depend on x2. So I have to choose some peculiar form for v. But this h1 is just minus h bar squared over 2 m1, let's say, del squared by del x1 squared. h2 will be minus h bar squared over 2 m1 d squared over dx1 squared plus minus h bar squared over 2 m2 d squared by dx2 squared. Well, this is, I would call this still a quantum mechanical problem where I have one particle can spontaneously go into two particles and two particles can spontaneously go into one particle. So there is particle creation and annihilation in this process. And this problem in particular happens to be one of the systems that I'm actually studying. So we seem, if you are interested, just look up X3872. And the eigenstates will be just such superpositions. So if you look at this state at a given moment, there's a finite probability that you will only see one particle, and there's a finite probability that you will see two particles in this system. Well, why restrict with two only? Well, no reason. We can go to 3, we can go to 4, we can go to 5. Well, then this description becomes quite cumbersome. So that is, field theory just presents us a very concise and intuitive means of looking at such systems where the number of particles need not be conserved, it can change. So that is one reason why we do quantum field theory. Well, I can also say that you already know one field theory, you have studied one field theory. Electromagnetism, that's a field theory. If you try to describe it in terms of photons, then you are quantizing it. Well, that is what we call quantum electrodynamics. That is one system that we will study this semester. So, but there what we do is we are used to thinking of electrodynamics as fields, the electric field, the magnetic field. Then we somehow try to interpret them in terms of particles. But one thing that quantum mechanics taught us was this is not limited to photons. For every system, you can interpret them as particles, or you can interpret them as fields. So although we are used in electrodynamics, we are used to thinking of electric and magnetic fields, then try to understand the photons, but the same holds for, let's say, electrons. We have a field corresponding to the electron, and then that field can also be described as the quanta of that field, which are the electrons, the particles we know. So we have, for everything, in fact, we have this, in a sense, this dual description. You can describe all kinds of particles, either as particles or as fields. Not both, by the way. If you are talking about electric field, magnetic field, you don't talk about photons. If you talk about photons, you don't talk about the electric. Well, you can calculate the corresponding electric field, etc. You can calculate the corresponding quantities, but if you choose your description to be in terms of photons, stick to it. If you choose to describe your system in terms of fields, again, stick to that description. Well, there is another field theory that you should have studied in significant detail. It's so-called the 0 plus 1 dimensional quantum field theory. Where you did also describe particle creation and annihilation, the simple harmonic oscillator. So what do you do in simple harmonic oscillator? Well, we have the Hamiltonian. This is my one-dimensional simple harmonic oscillator. Well, I will use the units h bar is equal to c is equal to 1. Does anybody know the speed of light?
3.10 to the 8.
Approximately. What's the error bar in the speed of light? Okay, what's the error bar? Well, somebody said none, so 3.2 something. What's the error bar in the speed of light?
You're asking for the measurement error for speed of light?
Yeah.
There is no measurement error. That's the definition.
There's no error in the definition of the speed. There's no error in the speed of light because we define it to have that value. What is the error bar is in the definition of the meter. So we say that 1 meter is the distance light travels in such and such seconds. That's just how we define it. Well, just like I could have defined the speed of light as 2.99 something, well, I could have also defined it to be 1. See, it's just 1. Well, what would that mean? It would tell me that I will measure time in the same units as length.
If I don't have error bar for time, time and the meter. Meter has error bar, and if I don't, time also has an error bar. If I don't have, time has no error bar, can I define still the
time does have an error bar, because we define also the time as also the certain number of oscillations of the particle radiation of cesium. That's how we just count how many times it oscillates.
But if I don't have, then I cannot define the speed of light as the
But we do have the error bar there.
Okay.
Yeah, the same thing for h bar. Well, what this will tell me is, for example, this will basically tell me that I have a single unit. For example, I don't have separate distance and time units because C is 1. I won't have separate energy and time units because h bar is 1. So I can just pick up whichever unit you want. Typically, well, I'm a particle physicist, so I will stick with the convention that I will define everything in terms of energy. So the mass is energy over c squared, it's energy. Length is energy inverse. Time is energy inverse. So everything will have an energy definition, energy unit. And it will simplify all the h bars and c factors that I tend to forget anyway. So this is my harmonic oscillator in these units. Well, how do we solve this? Let me just factor out an omega. Why do I factor out an omega? Well, the main reason is because I know the answer. The secondary reason is, well, if you look at this problem, the mass has the units of energy. Omega has the units of energy. And, well, I can even get rid of, you see, m times x squared, they always appear together. I cannot, in fact, think of m separately, separate from x. But I can think omega is separate from x. And omega has the unit of energy. So that's the natural unit of energy for this system. So that is why I'm just factoring out an omega. What remains is unitless. You see, we are looking at nature. And in general, in SI units, at least, we use the joule as our energy unit. But well, nature basically doesn't care about joule. Nature, just as nature doesn't care about 1 meter. It's just artificial units that we have invented as human beings. For this problem, the relevant energy unit will be omega, or h bar omega. So everything written in terms of omega will look a lot simpler. So that's why I factor out omega. Well, let's continue. Well, this looks like the difference of two squares, let's say. Well, let me write it in that form: square root of m omega over 2, x minus I over square root of 2m omega d over dx. Now, this is nice if I'm trying to solve, because each of these factors is just a first-order differential equation. So I kind of simplified my problem, let's say. Let's look at these two operators. Let me give them some names. Let me call this A, dagger. Let me call this one A. One is the Hermitian conjugate of the other one already. Because remember, del over del x is not a Hermitian operator. It's an anti-Hermitian operator.
Is this one or I?
One.
And how come they are Hermitian conjugate of each other? There is no plan to compare.
What is the Hermitian conjugate of del over del x?
Minus itself. That's why we are putting I, so that it will be right.
The Hermitian conjugate of this one is minus itself.
And minus. That's why we are putting I, so that it is.
It becomes Hermitian.
Yeah. In this case, we didn't do that.
Well, if you want an I have two of them.
Oh, okay.
So you see, here I have an Hermitian operator. Here I have another Hermitian operator. One is plus I, the other one is minus I. So if I take the dagger, one becomes the other one. Well, of course, I kind of cheated. You see, a dagger A, you see, in this step, it's not strictly correct. If x and the derivative and the x itself, they don't commute. So I cannot really do this. I introduced an error over there. Let me see how much error I introduced. Let me just multiply them out. So if I multiply these two, I get m omega over 2x squared. If I multiply these two, I get minus 1 over 2 m omega d squared by dx squared. Then I have the cross terms, which will give me, well, let me put them back, minus 1. The plus 1, the cross terms will give me plus 1 over 2 x d by dx minus d by dx times x. This is my a dagger times a. This is, these two terms is just 1 over omega times my Hamiltonian. Then here I have, well, this one, remember, the derivative operator acts everything that would come to the right of it. So it acts on x, and it also acts on whatever would come later on. So this product is actually x times d over dx plus 1. So these two will cancel. Okay, let me put it this way. Those two will cancel, so I will have minus 1 over 2. Oh, sorry. The other choice was correct. So H is just omega a dagger a plus 1 over 2. This is the correct form. Now, how to determine which one is A, which one is a dagger? I mean, if you don't know the answer, or if you just forget which one is A, which one is a dagger, you should check the commutators. This should be 1. Let's see, H, a dagger, would be omega, and H, a would be minus omega. Now, why will those be important? You see, we now have all these annihilation and creation operators. If you look at this commutator, that tells me that H, a dagger, minus a dagger H is omega a dagger. If you act it on an energy eigenstate, H A dagger acting on the state minus A dagger E, the energy eigenstate, is equal to omega A dagger, the energy eigenstate. So if you just combine them, H A dagger E, just move the second term to the right hand side, what you will get is E plus omega A dagger E. So if E is an energy eigenstate, A dagger E is also an energy eigenstate with energy E plus omega. Similarly, H A E would be E minus omega A E, just like E A operator lowers the energy by omega, A dagger operator increases the energy by omega. So now we actually have two different descriptions of the same system. On one hand, we have this description. We have this description on one hand, which we have this oscillator which just goes back and forth. And now, in terms of these A and A daggers, we have an alternative description in terms of energy packages. I have one energy package, two energy packages, three energy packages. I can add energy packages by A dagger operator. I can remove energy packages by the annihilation operator. So although I just started with a simple harmonic oscillator, now what I obtained was I have a system where I can create energy packages or destroy energy packages. Now let me ask you, what's a particle? We all have an understanding of what a particle is. Can you describe it? What's a particle?
Energy packets.
Well, that's the only thing we have. So we have our detectors. That detector can be your eye, by the way. It doesn't have to be a fancy electronic detector. Your eye, your hands, your ears, they are the detectors. What we hear, what we observe is energy packages and also momentum. Basically localized energy. That's what we call a particle. Now here we have a system where we have energy packages. So I can describe exactly the same system as one mass, capital M, moving back and forth. That's the oscillator. The same system is just, if you like, a storage of these energy packages, each having an energy omega, or h bar omega. You can add more packages or remove the packages. Why it is 0 plus one dimensional? Well, this system of packages evolves in time, but they're not moving anywhere. They don't have a position. They're all at the same place. That's why it's 0 dimensional. You had a question?
Why model it as a simple harmonic oscillator? Why not an non-harmonic oscillator?
Well, if you can do it, that would be great, but we can't do it.
Why?
It fails. You see, that was the reason why I started from this one, and then I have this factorization. In the case of an anharmonic oscillator, I don't have such a factorization. It just doesn't work. It becomes the anharmonic terms. In fact, that's a nice question. What happens with the anharmonic terms? Because here I just ignore the anharmonic terms. Well, what will be anharmonic terms? P squared over 2m plus 1 over 2m omega squared x squared. These are the terms that we dealt with. Then I have, let's say, lambda x to the 4. I don't add x cubed because it's not bounded from below. Potential energy has to be bounded from below. So that's why I have the x to the 4. Well, what is x in terms of these annihilation and creation operators? Let me just ignore the coefficients for the time being. If we just add a and a dagger, the derivatives, they just disappear, and I get a term proportional to x with some constant. So in terms of the same a and a daggers, my Hamiltonian becomes omega a dagger a plus 1 over 2 plus lambda, let me put the tilde, all the coefficients are over there, a plus a dagger to the power 4. Let me open that term up. Well, if you write this in the exam, you will lose points, by the way. It's a nice thing to be the professor sometimes. The fourth power of a plus a dagger is not this term. Because a and a dagger, they do not commute. But I just don't want to write them all out explicitly. So, for example, this term, just this term will be a dagger cubed plus a dagger squared plus a dagger squared a dagger plus a dagger cubed a. I have 4 terms. If they would commute, I will get that 4. But since they don't commute, I don't get that 4. But as I said, I'm too lazy to write it down. You don't have that luxury in your homework, so do it properly. So what will this tell me? Well, let's see. What is the Hamiltonian? Well, it tells me how my system evolves. Right? So let's say that I start with a system, let's say in the ground state. There are no energy packages. Or let me put one energy package. There's one energy package in this system. This is at the time t equal to 0. What will be my state at the time t is equal to, let's say, epsilon? I created my system. I just wait for a very short amount of time. Well, Hamiltonian determines the time evolution through this relation. Well, t is epsilon. It's a very short amount of time. So this will be approximately 1 minus I epsilon h1. Which will be, well, there is 1 minus I epsilon. Now, h has 2 parts. Let me say h0 plus lambda h1. Well, h0 is this part. h1 is this part over here. What will I have is I will have 1 minus I epsilon omega 1 because of that h0 term. Then I will have all these terms acting on 1. What will be, let's just look at this term again. This term will give me a dagger acting 3 times. We'll create 3 more energy packages. A acting on once more will remove one of those energy packages, so that term will add 2 more energy packages. So I will get a term with 3 energy packages. Of course, I will have many other terms. So what happened? I started with a system with 1 energy package. After some time, now I have 3 energy packages. And also, let's look at this term, by the way. What will that term do? It will create 2 packages and destroy 2 packages. At the end of the day, the number of packages will not change. So there will be a contribution here to this term. Now, this is not such a nice example because there are no other particles, etc. But what this will correspond to will be interactions. So due to interactions, the number of particles will be changing. So that is why now I started with 1 package. I ended up, after a very short amount of time, I ended up having a system with 3 packages. Other terms will create 5 packages. If I wait longer, I will get contribution with 7 packages, etc. And at the same time, you see, this is if the state 1 was an eigenstate, as a result of the time evolution, I wouldn't get all the other states, but I would have just get one. One in the sense that I would have only had this state. So if you look at these terms, what do they give me? They give me e to the power minus I epsilon omega plus delta 1. So those interactions also change the energy. So this one state, without those interactions, only had the energy omega. Now their energy is omega plus delta, whatever delta is. So those interaction terms first create or destroy particles during the time evolution of my system. And furthermore, they also modify the energy of my single particles, single package system. Single package doesn't have an energy omega anymore. Its energy is omega plus delta. The energy also changed. Well, this energy will eventually become the mass. So interactions, we will see that interactions changes the mass of particles. Any other questions about this one? Well, this is not very interesting. It's kind of boring. There are some nice comments, but things are not moving around. We would like to describe systems where the particles are moving around. So at least here, this is a zero-dimensional system, 0 plus the time dimension. We should at least construct a one-dimensional system. Well, that basically means that we should add another quantum number to my system. You see, position is a quantum number. It's the quantum number corresponding to the position operator, at least in quantum mechanics. So the easiest, let's say, I have a Hamiltonian. Let me also set m to 1. I have a bunch of harmonic oscillators, if you like. Well, if you want to think of this also in terms of, I have, let's say, a one-dimensional atomic chain. Now, this is something we create in condensed matter systems. You get atomic chains of thickness 1 atom. So every atom is free to oscillate around its equilibrium position. Well, you would also like to add some interactions between the atoms. Let's say the easiest one would be 1/2 some k xi minus xj squared. Well, typically you have this one, but not that one. But let's see what this will give me. Each one of these will be I plus 1, I minus 1. Any questions? Well, let's give a break now. Our 1 hour is almost over. And after the break, we will start with this problem. So we already knew a zero-dimensional field theory. We looked at that. Now we are constructing something in one dimension. Yeah, you can basically do the same thing in 2 or 3 dimensions if you want, but 1 dimension will be simpler as a demonstration.
We say 0 plus 1 dimension, right? But the Hamiltonian contains x term. Yeah, I mean dx and m omega x, right? Does not,
So you see, this is a 0 plus 1 dimensional field theory. This is a 1 plus 1 dimensional quantum mechanics problem.